So let's conclude our discussion on general planar motion. We're still going to be using Newton's laws. The sum of the forces equals mass times acceleration. Of course, these are vector quantities. And the sum of the moments, which is also a vector quantity, equaling I alpha. In the previous examples when we've done this, we've had objects which were moving, but we needed to use the moment equation because they were extended bodies. And like the bicycle example, perhaps we had a different normal force on the front tire than the rear tire. But now we're going to look at problems where they are rotating, and so an angular acceleration may or may not exist in that system. So let's take a look at this as a first example. We have a uniform slender rod with a mass of 0.235 pounds per foot. That's actually a weight per unit length. And it makes this assembly which contains a spoke. I'll consider this part to be the spoke. And then the ring, which is the outside part. Now the center of mass of the ring is located at point A, the center of the system. The center of the mass of the spoke is at the middle of the spoke. Because it is a uniform density, then the mass will be uniformly distributed, so the center of mass of that spoke is in its middle. So the assembly is rotating clockwise, and it has a constant rate. Now that's important. The omega is equal to 120 RPMs. That's rotations per minute. So that's 120 times 2 pi radians divided by 60 seconds. And so that's 4 pi radians per second. And that's a constant. And the reason that that's so important is that means that alpha is equal to 0. So this thing is going to be rotating with a constant angular velocity. Now notice that gravity comes into play. So this is in the vertical plane. So in its current position, the gravitational force is pulling down. That's the mass of the spoke times g. And that force wants to make it spin faster as it rotates in this direction. But what this moment is doing is it's keeping that from increasing. So the moment is actually working against gravity in the position that you see right here. Now there's also a gravitational force here. That's the mass of the ring times g, because the center of gravity for the ring is right in its geometric center, and that's where A is located. Then there's going to be a force here at the pin. I'm going to call that A sub x, and also a force at the pin A sub y. And those combine to give me a normal force due to the pin acting on the assembly. The gravitational forces are of course due to the earth acting on the assembly. And then there's this moment m, and that moment is not constant, and so what we're interested in is what is that moment, and we're going to find that as a function of theta. Then we're going to have the accelerations. Now the ring is fixed at its center, but the spoke itself will have an acceleration. But remember that alpha is equal to 0, which means any tangential acceleration, A tangential, that's equal to 0. It's neither speeding up nor slowing down. So the only acceleration in this scenario is in the normal direction. Okay, so let's examine that acceleration. It's in this direction. There's going to be an x component and a y component. So the magnitude of the acceleration is r over 2, where this 8 inches is that r. And so this is only halfway out, so that's 4 inches, times omega squared. This is the angle theta here. So this will be r omega squared over 2 times the sine of theta, and this will be r omega squared over 2 times the cosine of theta. So that's the y component and the x component. So if I look at my force equations, the sum of the forces in the x, I only have A sub x, and that's going to equal the mass of the spoke times r omega squared over 2 sine theta, and that points left. So A sub x will actually point to the left in that scenario. So you'll notice that A sub x is a function of theta. Everything else in here is constant. Omega is constant, the radius of 8 inches is constant, the mass of the spoke, which I can get from here, that's constant. So the mass of the spoke, let me say the weight of the spoke, will equal 0.235 pounds per foot, and then it's 8 inches long, so that's 2/3 of a foot. So that'll give me the weight of the spoke, and of course I divide that by gravity to get the mass. The sum of the forces in the y direction have A sub y minus the mass of the ring times g minus the mass of the spoke times g, and that will equal the mass of the spoke times r omega squared over 2 cosine theta, and of course that's down, so put a negative sign there. And again, everything here is known except for A sub y, so I can find A sub y as a function of theta. So So those are easy to do. Then we'll look at the moments. And I'm going to sum my moments about the center right here at A. Because if I do that, AY, AX, and the mass of the ring all go away. And the only thing I'm left with is the moment due to the mass of the spoke times G. And I'll need to multiply that by this distance here. But again, this triangle, here's 4 inches. There's the distance I'm interested in. And this is the angle theta. And so what I'm going to get for the sum of the moments acting at A, I'll get the mass of the spoke times r over 2 sine theta, and that will give me a clockwise moment. And we'll add to that, and actually we'll subtract because it's also clockwise m, and that will equal I alpha. Now I'm going to say plus r cross ma, but keep in mind the only ma that existed was along the radius. So r is out, the ma is in, this cross product will be 0. Also remember alpha is equal to 0, so I don't even need to worry about what is the moment of inertia of this system. It's undergoing constant rotation, so alpha is 0. And so what we end up with then is m equaling minus the mass of the spoke, r over 2 sine theta. And so now the moment is known as a function of theta as well. So a sub x, a sub y, and the moment are all functions of theta. And we can solve those for the given thetas or for any theta arbitrarily given. Okay, let's take a look at this example. This is a really important example because a lot of things are going on here that we really need to think about. So I've got a drum wheel combination. The drum has an inner radius of 80 millimeters. So that's right here, and I'm going to call that r inner. And then the wheel itself, the disc, has an outer radius, r outer, and that's 160 millimeters. Okay, the combined mass is 5 kilograms. The radius of gyration is 120 millimeters. So the moment of inertia is 5 kilograms times 0.12 meters. That's 120 millimeters, and we square that. And so that's 0.072 kilogram meters squared. Okay, there's a cord being pulled with a tension of P, and that's equal to 20 newtons. And you'll notice that we're given a static coefficient and a kinetic coefficient. Now this is really important. And it goes to part A. This question always needs to be asked in a question like this. Is the disk sliding or not? Because that'll make a big difference. If the disk is not sliding, if it's rolling without slipping, then I can say the acceleration is equal to r alpha. If it's rolling without slipping, acceleration is equal to r alpha. But if there's sliding taking place, then this is not equal to r alpha. If there's not sliding, if it's rolling without slipping, then A is equal to r alpha, but the frictional force is static, so I don't really know what it is, because remember the static frictional force is less than or equal to mu static times the normal force. So these equations hold if it's rolling without slipping, but if slipping is taking place, A is not equal to r alpha, but then I do know that the frictional force is kinetic, and that's equal to mu kinetic times the normal force. Alright, so we need to start with a force diagram. So I've got a gravitational force, mg, and that's due to the Earth, acting on my system, the drum and the disc. There's a tension to the right of P, that's 20 newtons. That's due to the cord acting on my disc drum system. There's a normal force here at the bottom. That's due to the ground acting on the disc drum system. And then there's a frictional force. Now, the question is, what direction is the frictional force? Well, let's assume that that's not even rotating. I'm just dragging it to the right. So if I'm dragging it to the right, the frictional force is to the left. But what if I'm not dragging it? What if it's sliding? So if it's sliding, let's say I'm pulling it hard enough that there's slipping taking place, then it's going to slip in this direction. In other words, it's spinning around in this direction really fast. So that means it's sliding against the surface to the right, and so the frictional force is always against the sliding, so it must be to the left. So in any scenario, the frictional force is to the left here. So that's a frictional force due to the ground acting on the drum disc system. Great, so now I'm ready to draw out my equation. So the sum of the forces in the y, that's the easy one. I'm going to have a normal force up, and mg is down, and there is no y acceleration that's equal to 0. The acceleration of this system is strictly in the x direction. So there's my ma. So the sum of the forces in the x direction, I get the tension P to the right, and the frictional force is to the left. I don't know if it's static friction or kinetic friction, so I'm leaving that blank. And that's going to equal mass times acceleration. I don't know the acceleration, I don't know the frictional force, two unknowns. I know the normal force is equal to the weight, so we go to the moment equation. Now to make my life simple, I'm going to sum the moments here at g, because when I do that, mg, which is straight down, contributes no moment, ma, which is emanating from g, contributes no moment, and fn down here goes straight up and it goes through g. And so the lever arm for Fn is 0, so it contributes no moment. So when I do the moment equation, summing them about g, I'm only going to get P times R inner, and that's trying to rotate things counterclockwise, so that's positive. And then F times R outer, that's trying to rotate them clockwise, so minus F times R outer, and this will equal I alpha. So I don't know F, I don't know A, and I don't know alpha, but I now have two equations, and since I'm assuming no slipping, A is equal to R alpha becomes my third equation. So let's rewrite the equations. I'm going to get F plus 5 kilograms times acceleration equals P. That was my X force equation. As I look at the moment equation, I'm going to bring the F R outer to the other side, and I should take note this thing is moving to the right, so the acceleration, the angular acceleration, is in that direction. So I'm going to put a minus sign out in front of my I alpha there. So I get 0.16 meters times F minus 0.072 kilogram meters squared times alpha. And all of that equals P times R inner, so 20 newtons times 80 millimeters, which is 1.6 newton meters. And that was positive, so we'll leave it that way. And then finally, A equals R alpha means A minus R alpha equals 0, but which R? See, now this point right here that the chord is attached to, that's moving to the right. That's not a fixed point. Alpha is in this direction, and so the fixed point would be down here, and so the R that I use for R alpha is going to be the outer radius, so 0.16 meters. So I have a system of three equations and three unknowns. P here, by the way, is 20 newtons. So when I solve this out, I get F is equal to 13.6 newtons, A is equal to 1.28 meters per second squared, and alpha is equal to 8 seconds to the minus 2, which is the same as radians per second squared. So now we need to analyze F. Keep in mind the normal force is equal to mg. M is 5 kilograms, G was 9.81 meters per second squared, so that's 49.05 newtons. So F static is less than or equal to 49.05 newtons, the normal force, times 0.25, the coefficient of static friction, which is 12.26 newtons. Now the frictional force is 13.6 newtons, so that's bigger than this. So the frictional force has exceeded my maximum static frictional force. Therefore, since F is greater than F static, then that must be slipping. So what that means is I have to re-examine my equations. Now keep in mind the X equation said that P minus F, which now I know is kinetic, is equal to MA. Well, the kinetic frictional force is 49.05 newtons. That's the normal force still, times 0.20. That's the coefficient of static friction. So that's 9.81 newtons. So 20 newtons minus 9.81 newtons equals mass times acceleration. So 10.19 newtons equals 5 kilograms times acceleration. So the acceleration is equal to 2.038 meters per second squared. And then I'll still use my moment equation to calculate out alpha, but I now know this term and this term. So that's 20 newtons. So that's 20 newtons times 0.08 meters. That's the moment due to the tension. That's counterclockwise. Minus the frictional force, which is 9.81 newtons, times 0.16 meters. And this will all come out to be 0.0304 Newton meters, and that's equal to 0.072 kilogram meters squared times alpha. And so alpha is equal to 0.422 seconds to the minus 2. And that actually is going to be counterclockwise. So the angular acceleration is opposite the direction you might think. So it's actually unwinding a little bit as it slips. And that makes sense, because remember we said it would be slipping in this direction. So really that positive alpha does make sense. Okay, let's take a look at one more example here. I have a gear with a mass of 5 kilograms. That's gear C here, and it's attached to a uniform bar with a mass of 3 kilograms. Gear D is a ring gear, and that's a stationary gear. Now that's important because now I know that there's a point here, and we're going to call that point D, and that's stationary, and of course we already know point A is stationary. The system is released from rest. We want to determine the angular acceleration of gear C and the acceleration of point B. So we're going to start off with a force diagram. I'm going to have an mg here. That's a bar, so I'll call that m sub b g. And the gear, m sub g, g. Force here, we'll call that a sub y. And there's going to be a force up here. We'll call that fd. Now that's actually going to be, well, it's really a normal force as the gear teeth come together. So that's due to the ring gear D acting on gear C. A sub y is a normal force due to the pin at A acting on the bar, and we'll consider the bar gear C system to be a combined system. Now we're interested in the angular acceleration of gear C and the acceleration of B, so we kind of need to look at this, and let's think about last chapter again. As this thing is released from rest, clearly it's going to rotate in this direction. It's going to rotate in the clockwise direction. What that means is the acceleration of B with respect to A is going to equal alpha AB crossed with the position of B with respect to A. So we can't forget that stuff from chapter 16. That's still important. Minus omega of AB squared times the position of B with respect to A. But omega is equal to 0, so I don't need to worry about that part. So that's the acceleration of B with respect to A. The acceleration of D with respect to B is going to equal alpha of gear C crossed with the position of D with respect to B. And again, minus an omega squared, but that's 0, so I don't need to worry about that. But when I add these two terms together, that's the acceleration of D with respect to A, but that's equal to 0. So 0 equals alpha AB, which I'm going to assume is in the positive k direction, crossed with 0.2 meters in the I hat direction, plus alpha C, which I'll also assume is in the positive k direction, crossed with 0.1 meters in the I direction. Well, k cross I is j, and so I get 0.2 meters alpha AB plus 0.1 meter alpha C equals 0, and so I can say that alpha AB times 2 equals minus alpha C. So if alpha AB is counterclockwise, alpha C is clockwise. But in fact, if this thing is falling due to gravity, which we would anticipate, alpha AB is actually negative, and so alpha C will be positive. And that makes sense. If this goes down like that, it's dragging B down, and so this has got to rotate in this direction around B. And so that's counterclockwise. So AB is moving clockwise, gear C will move counterclockwise. So they're in the opposite direction. That's exactly what that sign would tell us. Okay, so let's go ahead and solve this equation out. Let's just take a look for a moment as far as doing the moments go. Let's just take a look at gear C. So if I isolate gear C, it's free to fall. Bar AB is not going to be pushing it up or down. Bar AB might have a force acting at B, but if I do the sum of the moments about B itself, then there are no moments at B, so those forces are fine. The gravitational force, the weight of the gear, is down, and that's at B, but that doesn't matter because that's right at B. This weight over here for the bar doesn't count because it's not part of the gear. So all we really have is FD here. And so the moment is going to be FD times the radius, which is 0.1 meters, and that's going to equal I alpha of the gear C. The gear has a mass of 5 kilograms, so the moment of inertia is 5 kilograms times the radius of gyration, which is 0.075 meters. And that's all squared. So I get 0.075 0.28125 kilogram meters squared, and so F sub D equals 0.28125 kilogram meters, okay, because I've divided both sides by this 0.1 meters times alpha C. Keep in mind alpha will have units of seconds to the minus 2, so this is kilogram meters per second squared, which is a force, so that works out fine. So let's take a look again. Here's a sub x and a sub y. I know there's the mass of the bar there times g. There's the mass of the gear times g there. And now we've got F sub D here. And the bar has a mass b times a, and there's a mass of the gear times a there. This is a at point B. So this acceleration, that's at the middle of the bar, so I'm going to call that a sub b, little b for the bar. And since that's a fixed object, it's pretty clear that a sub b will be 1/2 a sub big B, or a sub big B will equal twice the acceleration of the center of gravity of the bar. So the sum of the forces in the y direction, I'm going to have a sub y plus fd minus m sub b g minus m sub big G g, and that'll equal m sub b a sub b plus the mass of the gear times the acceleration of the gear, which is twice a sub b. There's really no x forces, so that's not needed. And then let's just do a sum of the moments about a. So I'm going to get the mass of the bar times g times 0.1 meters. And that's clockwise, so that's a minus sign. Minus the mass of the gear times g times 0.2 meters plus f sub d times 0.3 meters. And all of that's going to equal I AB times alpha of AB plus I of gear C times alpha of C minus m sub b a sub b times 0.1 meters minus m sub g twice a sub b times 0.2 meters. And those are the systems of equations that I can then solve out. One quick change, this has to be negative there. And that should be about it. And when I take this equation, combine it with this equation and this equation, then I should get alpha AB equal to 72.4 radians per second squared. 72.36 actually, and this is negative, it's in the clockwise direction.